Okay, now let us turn our attention to something new. We're now going to put both of the two elements we have studied together in the same circuit, the resistor and the capacitor. Remember the capacitor? Okay, what are we doing here? We put a resistor and a capacitor in series with a battery. Okay, at time t equal to 0, we assume at that moment the capacitor has no charges deposited on these two plates. In other words, at that time it is not charged at all. It's completely discharged. Okay, but at that point we start to let a current flow through it. Here's a current flowing from positive to negative terminal of the battery. I want to know what happens. I want to know what happens to the current. Okay, let's first study this qualitatively, and then we can study it quantitatively. First, qualitatively. In the beginning, there were no charges on these two plates. Okay, so what is the voltage difference across this guy? 0, right? 0. So therefore, you can effectively short circuit these 2 points, assuming it's just a wire. For at least for that moment, it's not going to make any difference because there is no potential difference anyways. And the only load of the circuit is then R. You get an epsilon applied on this R. What kind of current you're going to get? What is I initial or I naught? That would be what? Epsilon of R, right? For that moment. Now, this is not going to last forever, however, because as time progresses, as the current flows, the charges will get accumulated on this plate. It's got no place to go. It cannot fly from here to there, so it's going to be an accumulation of charge here, an accumulation of negative charge there. Now, there will be a potential difference between these 2 points, and that potential difference points backwards, right? Here, because you get positive here, negative there. It fights against this EMF, which has a positive here, negative there. So as a result, the current will gradually diminish. Okay, that also makes sense if you think about it another way, and that is, you originally got no positive charge here, so it is easy to put some more positive charge here. But you already have a lot of positive charge here. You want to continue to bring even more positive charge, you're going to have to fight against the existing positive charges, because positive and positive charges will repel each other, right? So the task will become more and more difficult. Okay, as a matter of fact, after long enough time, there will be enough potential difference between these 2 terminals that the potential difference over the capacitor would be the same as epsilon, except it points backwards. So what is the net EMF that drives the entire system at that point? It would be 0, right? So the current will then reach what? 0. It's going to diminish to 0. And that is when we say the capacitor is fully charged. Okay, so no more current. This is what's called a charging circuit. Okay, so in this process, the current keeps on flowing this way, but the magnitude of that current diminishes over time. Eventually, the current will stop, will reach 0, and there are a lot of charges on this plate and that plate. We say the charging process is complete, and the capacitor is said to be fully charged. That is the qualitative description. Now we can plot the current qualitatively as a function of time. Okay, as a function of time, and this is what you're going to see. You start with I naught at t equal to 0, and the current will drop over time. Okay, it's going to drop over time. Now, is it going to drop like a straight line? Is it going to drop like a straight line? Well, not quite. Okay, if the current drops like a straight line, then there will be a moment where the current is exactly 0 over a finite period of time from here to there. In reality, what happens, imagine when the charging has been going on for quite a while, this capacitor is nearly fully charged. Okay, not quite fully charged, but nearly fully charged. So there's only a tiny difference in the potential difference here and the voltage there. EMF is only slightly greater than that. So at that point, the current flowing through will be extremely small. Okay, when the current flowing through is extremely small, that will slow down the charging process. So it's going to take a lot of time for enough charge to deposit on it, so that the difference between this voltage between this delta V and this EMF completely goes down to 0. So as the charging goes on, it's going to take longer and longer time for the same amount of charge to flow through. So you can imagine the current will not die down immediately. Rather, it's going to do something like this. Okay, eventually we will go down to 0, but the current will not diminish as a straight line, rather it diminishes. The rate at which it diminishes gets slower and slower and slower, because as the capacitor approaches fully charged state, the current, it's going to take more and more time to deposit more charge on it, and so it takes a long time. Okay, it takes a long time for the current to diminish, because the current will go to 0 only if this delta V and the epsilon become completely equal to each other. So it goes down like that. Right? It goes down like that, starting from epsilon over r, which is I naught. Now we can of course calculate the exact shape of this curve, which we will do in just a minute. Okay, but what I want to know is, based on our gut feeling, based on our physical intuition, what do you think this thing should be? Okay, what can we say about this curve? In fact, you can also plot the voltage across the capacitor, Vc. Okay, Vc, that is this voltage minus that voltage, the potential minus that potential. Initially, Vc is 0, okay, when it's just start charging, but gradually, Vc should approach what? Epsilon, right? In fact, when Vc equals epsilon, everything is fully charged, the capacitor is fully charged, there is no current flowing anymore. That's when the current goes down to 0. Okay. Can I find the curve for this I? Can I find the curve for Vc? In fact, if you know one, you will find the other. Now, before we use a mathematical equation to fully figure out the exact shape of this curve and that curve, let's look at intuitively what should we be getting. Look at this curve here. This curve starts from a finite value and gradually diminishes to 0. But it won't reach exact 0 mathematically until t equals infinity. What does that remind us? Have you learned a simple math equation that behaves like that? Well, you probably can recall such a monotonically decreasing equation. That will be an exponential equation, exponential function, right? And it's an exponential function with what? With a negative index. It cannot be e to the power something t, because that will go to infinity. Rather, it's e to the something negative t. Okay. So you gotta have a constant in front of that. Okay, you gotta have a constant which I call alpha in front of that. There gotta be an alpha, because t is not a dimensionless number. And yet e to the power x, that x as a whole must be dimensionless. Okay, must not contain any units. So you got e to the negative alpha t. E to the negative alpha t is a function which starts from 1 and going down to 0. That looks just like that, except our case, the current does not start from 1, it starts from I naught. So how about I equals I naught times this? Okay, how about this? That sounds reasonable, but we don't know it for sure if it is right. What about this Vc here? Okay, what about this Vc here? Well, Vc we also know roughly, qualitatively, that it starts from here, ends up there. That also looks kind of like an exponential function with a negative index. So how about if I guess Vc to be something like e to the negative alpha t? Again, we start with something like that. But e to the negative alpha t is a function that goes from the largest value, which is 1, and it goes down, it doesn't go up. Okay, so it's a function that goes like this, right? How do I make it go up? I have to flip it. Okay, I have to flip it. So how do you flip it? You add a negative sign. Now when you add a negative sign, this function will now become something like that. It does go upward, but it starts from negative 1, right? This thing starts from negative 1, not from 0. So how do you let it start from 0? You lift the whole thing up by 1 unit, so you get something like that. Okay, this whole thing starts from 0 and will reach what? Gradually, over time, reach what? Reach 1, and that is when t goes to infinity. Right? When t goes to infinity, e to the power negative alpha t is 0, so it becomes 1. Okay, so it goes up like that. But in our case, we want to reach what? We want to reach epsilon. Okay, we want to reach epsilon, or Vc maximum. I say Vc maximum. Of course, Vc maximum would turn out to be epsilon. That is what we believe Vc should look like. We don't know for sure if it's right or wrong. Okay, but that's at least our guess. Now, we do not know at this point what alpha should be, except we do know the unit of alpha. the dimension of alpha, that must be what? That of 1 over time, okay? Because alpha times t is dimensionless, remember that? Okay, but we also know that alpha should be a function of r and c. Okay, should be a function of r and c. It should not, however, be a function of epsilon. We know that even before our calculation. How come it's not a function of epsilon? Imagine if everything else is the same but you double epsilon. Okay, when you double epsilon, what happens to the current when r and c are all the same? We get twice the power driving the current, so the current will be doubled, right? The current will be doubled. However, the time it takes to complete the charging will still be the same, because remember, you're gonna have to charge the capacitor to twice as much charge as before, because the final value of the potential difference is now 2 epsilon, not 1 epsilon. So you double the final charge potential difference, you also have to double the final charge. So you see, you have twice as much current reaching twice as much final charge. Isn't it true that total time will be the same? Okay, so changing epsilon will not affect charging time, but obviously alpha is something that can determine the charging time. If alpha is large, for example, what does that tell you? It tells you that the current will quickly diminish to 0, okay, and the VC will quickly go up to maximum, which means the charging will be fast. So alpha obviously determines charging time, and charging time has nothing to do with epsilon, as we just saw. So therefore, alpha should not be a function of epsilon. It should be a function of r and c. The question is, how is alpha related to r and c? Okay, before we find it out formally, let's try to make a guess. Our job is to find a combination of r and c that will give you the right dimension, which is 1 over time. Okay, 1 over time. How do we do that? Well, I claim that this combo 1 over RC works out. Okay, unit-wise at least it works out. This is in ohm, this is in farad. What is the equivalent of 1 ohm times 1 farad? 1 ohm times 1 farad. I say, in fact, it is 1 second. Okay, ohm has never met farad, and yet we multiply them together, we get 1 second. All right, how does that make sense? Well, let's see here. Is that true? Let's manipulate this expression a little bit using equations that we already know. For example, ohm, that is volt per what? Volt per current. Okay, volt per amp, so that's 1 volt per amp. Amp is a charge over second. Okay, what about farad? Farad is what? The unit of capacitance, and that will be charge, that of charge divided by that of potential. So there will be C, coulomb, divided by V. Okay, you see, C and C cancels, V and V cancels, 1 over second. That is in fact second. So that makes sense. Okay, so at least dimensionally speaking, alpha should go like 1 over RC. Of course, this may not be completely unique. It could be 2 over RC. It could be pi over RC. Who knows? Okay, but it's got to be something times 1 over RC, because it's the only way to get it correct unit-wise. And this also makes sense from physical point of view, not just from a unit point of view, because after all, a large alpha means the charging process will be short, right? Because it can go down quickly and keep it go up quickly. But a large alpha means a small r and a small c. So if this expression makes sense, that would mean that a small r, small resistor, and a small capacitor would be charged up quickly. Now, is that right? Look, first of all, you have the small resistor. A small resistor promotes a large current, so that will make the charging faster. And a small c, what does the small c tell you? A small c means it cannot hold a lot of charge. Okay? So you give it a little bit of charge, it's already fully charged. So you see, on the one hand, with a low R, you have a large current, and on the second hand, you only have a little bit of current, a little bit of charge to fill, and therefore, overall, the charging process would be fast. It makes sense. Okay, so it makes sense physically that alpha should go like 1 over RC, not RC. Okay. On the other hand, you can imagine if R is large and C is large, then the charging process will be slow. Okay, so it should go down like this slowly, and here it's go up slowly like this. Why? Because A large R means a very small current, and large C means you got a lot of charge to deposit before it fully charges up. So that takes a long time. Okay, using a small current to fill a very large capacitor. So this is our qualitative understanding. With only our physical intuition and our guess, we got pretty detailed answers. Of course, we won't know for sure whether these are right or wrong until we fully solve the problem. And the way we solve this problem is nothing more than Kirchhoff's rule.